am Dr.G.B.Chandra, Assistant Professor of Mathematics, Department of Freshman Engineering, Aditya University. Now on linear differential equations of higher order, in this we'll see the particular integral of linear differential equation of the form f of d of y is equal to q of x, where the right hand side q of x is in the form x into v of x. So for this we'll see the particular integral evaluation rule. That is one outcome of this. And the second outcome is the method of variation of parameters, which is a general method to find particular integral of a second order linear differential equation. These two are our learning outcomes for this. Now, the general solution of the linear differential equation for the form f of d of y is equal to q of x is given by y is equal to, so here y is the unknown function in this equation, which is the dependent variable, and that is given by y is equal to complementary function plus particular integral. And the formula for the particular integral of this equation is given by yp is equal to 1 by f of d of q of x. So for different q of x values, we have different rules. Until now, we have seen the case when q of x is e power ax plus b. We have seen when q of x is equal to sin ax plus b or cos ax plus b, and q of x is equal to x power k polynomial in x, and q of x is equal to e power ax into v. Now we'll see the next case where q of x is equal to x into v of x. So for different functions, we have different rules for evaluating the particular integral. Now when q of x is equal to x into v of x, the particular integral is yp is equal to 1 by f of d of q of x for the given equation, and q of x is x into v of x. So the evaluation has a formula which is given by yp is equal to x minus f dash of d into 1 by f of d of 1 by f of d of v of x. So this is the formula for yp when q of x is x into v of x. Now we evaluate this from the right of this expression, which means first we evaluate 1 by f of d of v of x based on the function v of x. So when v of x is a sine function or a cosine function, we apply that particular rule. Now after evaluating 1 by f of d of v of x, that is operated on both these terms within the brackets, like x into the resultant minus f dash of d into 1 by f of d of resultant. So again, those particular rules are applied for the evaluation of these two terms. Now we will apply this for this example. Solve d square plus 1 of y is equal to x into cos 2x. So our main concentration is in the particular integral part, where this is in the form x into v of x. So x into cos 2x. So given that y is equal to 0 and dy by dx is equal to 0 at x is equal to 0. So this is the condition that we have to apply on the general solution of this equation. So we have to solve the differential equation satisfying these conditions. These are called initial conditions. So at x is equal to 0, y is 0 and dy by dx is equal to 0. The given equation is d square plus 1 of y is equal to x into cos 2x. So comparing this with f of d of y is equal to q of x, f of d is d square plus 1, q of x is x into cos 2x. So CF or YC, so d square plus 1 of y is equal to 0. For this equation, auxiliary equation is f of m is equal to 0. So that is will give you m square plus 1 is equal to 0. And we can find the roots of this by the formula. And we'll get the roots as here, m is equal to plus I and minus I, imaginary roots. So writing them in the form alpha plus or minus I beta. So I can be written as 0 plus 1 into I. Minus I can be written as 0 minus 1 into I. So here, if you compare this with alpha plus I beta, so alpha will be 0 here and beta will be 1 here. So in this case, YC is given by e power alpha x into C1 cos beta x plus C2 sin beta x. So alpha is equal to 0 is substituted and beta is equal to 1 is substituted. So YC will give you e power 0x is 1. So C1 cos x plus C2 sin x. Now particular integral yp is equal to 1 by f of d of q of x. F of d is d square plus 1, q of x is x into cos 2x. Now the evaluation formula is for 1 by f of d of x into v of x, it is x minus f dash of d into 1 by f of d of 1 by f of d of v of x. So substitute all these functions. So f of d is d square plus 1. F dash of d will be derivative with respect to d, which will be 2d plus 0, which is 2d. So substitute f and f dash in this. So we'll get yp is equal to x minus 2d, which is the derivative, into 1 by d square plus 1 of 1 by d square plus 1 of cos 2x. Now we have to evaluate 1 by d square plus 1 of cos 2x. Okay. Now for cos 2x, the rule is put d square is equal to minus 2 square. So minus 2 is the coefficient of x in this cosine function, so which is minus 4. So that will give you yp is equal to x minus 2d 1 by d square plus 4 of 1 by minus 4 plus 1 of cos 2x. So minus 4 plus 1 is not equal to 0. So it is minus 3. So we write that before the function. So yp is equal to minus 1 by 3 into, now multiply cos 2x with both the terms. So x into cos 2x minus 2d 1 by d square plus 1 of cos 2x. Cos 2x is multiplied with both the terms in the brackets. Now next we again evaluate the second term in this bracket, which is 1 by d square plus 1 of cos 2x. So we have d in the numerator, d square plus 2 in the 1 in the denominator. We operate one after the other. So first we operate 1 by d square plus 1 on cos 2x. For this, again the rule for cosine function is d square is equal to minus 2 square, which is minus 1. So that will give you minus 4 plus 1 in the second term here in the denominator. So which is minus 3. So this will give you minus of minus 3 plus, so yp is equal to minus 1 by 3 x into cos 2x plus 1 by 3 2d of cos 2x. Now d stands for d by dx. We are operating d in the numerator on cos 2x. So d stands for d by dx of cos 2x, which is derivative. So yp is equal to minus 1 by 3 x into cos 2x plus 2 by 3 minus sin 2x into 2. So multiplying will give you yp is equal to minus 1 by 3 x into cos 2x minus of minus, it will give you plus 4 by 9 into sin 2x. So the general solution is y is equal to yc plus yp, which is y is equal to c1 cos 2x plus c2 sin 2x minus 1 by 3 x into cos 2x plus 4 by 9 x into sin 2x. So here c1, c2 are arbitrary constants. They can be any constants. So this general solution will represent infinite number of solutions. So for c1, c2 values, these represent infinite number of solutions. Now from this, we have to find one particular solution which satisfies the given conditions. So this is y. Now differentiate this solution with respect to this equation 1 with respect to x. So dy by dx will give you, so c1 into cos x derivative is minus sin x plus sin x derivative c2 into sin x derivative cos x minus 1 by 3. For x into cos 2x, we have to apply product rule, uv rule. X into cos 2x derivative minus sin 2x into 2 plus x derivative into cos 2x, 1 into cos 2x plus 4 by 9 into sin 2x derivative is cos 2x into 2. Now simplifying this, dy by dx will give you equation 2. So multiply the terms and simplify this. Now the given conditions are at x is equal to 0, y is equal to 0. So sometimes this is also written as y of 0 is equal to 0. So this is the y value and this is the x value. So we have to apply this condition on y, which is given by equation 1. Now y is equal to 0 at x is equal to 0 is applied on 1. So 1 implies wherever y is there, you write 0, wherever x is there, you write 0. So left hand, the first term is 0, left hand side is 0, y c1 into cos 0 is 1 plus c2 into sin 0 is 0 minus 1 by 3 x into, that is 0 into cos 0 1 plus 4 by 9 sin 0 is 0. So this will directly give the value of c1 as 0. Now the second condition is at x is equal to 0, dy by dx is 0. So this is applied on equation 2. So because 2 represents dy by dx. Sometimes this condition is also represented as y dash of 0 is equal to 0. So this is the y dash value and this is the x value. So apply this condition on dy by dx, which is given by equation 2. So the left hand side of 2 is dy by dx, which is 0 minus c1 into sin 0, which is 0 plus c2 into cos 0, which is 1 minus 1 by 3 x is 0. So 0 into sin 0, okay, will give you 0 plus cos 0 1 plus 8 by 9 into cos 0 1. Directly we'll get the c2 value from this expression after simplifying, because c1 term is 0, and if you simplify this for C2 value, we'll get the C2 value as minus 5 by 9. So C1 is 0, C2 is minus 5 by 9. So sometimes you may get two equations in C1 and C2, and solving those equations we'll get the values of C1 and C2. Substitute C1 is equal to 0 and C2 is equal to minus 5 by 9 in the general solution given by y, that is equation 1. So y is equal to C1 0 cos x plus C2 minus 5 by 9 sin x minus 1 by 3 x into cos 2x plus 4 by 9 sin 2x. So y is given by minus 5 by 9 sin x minus 1 by 3 x cos 2x plus 4 by 9 sin 2x is the required particular solution. So out of infinite solutions, this is one solution or the particular solution which satisfies the conditions, the initial conditions, y of 0 is equal to 0 and y dash of 0 is equal to 0. So this general solution satisfies these two conditions. So that is the required particular solution. So this is the end of evaluation of the particular integrals, specific particular integrals. And the next one method is method of variation of parameters. This is again the method to find the particular integral or yp, and the importance here is, the specialty here is, it is a general method to find the particular integral, and this is applied for second order linear differential equations only. So for a second order linear differential equation, to find the particular integral, the general method is the method of variation of parameters. So when you say general method, we can apply this method for a second order linear differential equation to particular integral when q of x is any function of x. In the previous cases, we have discussed for only specific functions of q of x. Now, method of variation of parameters can be applied for any function of q of x. Only the restriction is it should be a second order linear differential equation. So the working rule for this method of variation of parameters is described here. So consider a second order linear differential equation of the form d square y by dx square plus a1 dy by dx plus a2y is equal to q of x. So a1, a2 are constants. It is second order. So q of x can be any function of x. Step 1. So we have to see that the equation is in this form, the standard form, d square y by dx square plus a1 dy by dx plus a2y is equal to q of x. Step 2. We have to find the solution of d square y by dx square plus a1 dy by dx plus a2y is equal to 0. Right hand side is equal to 0, which will give you the complementary function. So yc as c1 into u of x plus c2 into v of x. So it is written in the form of c1 into u of x plus c2 into v of x. Now from this we can identify u of x and v of x functions. From this form, u and v are identified. In step 3, we have to find the Wronskian of u of x and v of x, which is given by determinant of the first row has u and v, and the second row of this determinant has u dash and v dash, the derivatives of the first row. So expanding this determinant, we get u into v dash minus u dash into v. So this always should be not equal to 0 in our case. Now, after finding Wronskian, the fourth step will give you yp by the method of variation of parameters, as yp is equal to a of x into u of x plus b of x into v of x. So uv are the functions in yc, and we have to find a of x and v of x. So a of x is given by the formula minus integral v into q by w dx. So v is known, q is the right hand side, w is the Wronskian. So integration with respect to x, and b of x is integral u into q divided by w dx. So substituting u, q and w and integrating, will get b of x. So by the method of variation of parameters, yp is given by a into u plus b into v, where a is minus integral vq by w dx, b is integral uq by w dx. And the final general solution is given by y is equal to yc plus yp. So applying this for this example, so solve d square plus a square of y is equal to tan ax. So here by the method of variation of parameters. So this will be mentioned in the question, or observing this right hand side. Here right hand side is tan ax is not one of the specific functions that we have discussed earlier. So we have discussed only for sin ax plus b and cos ax plus b and not for tan. So this is not our specific function. So for this tan ax, we have to apply method of variation of parameters to find the particular integral. Now the first part is the complementary function. So write the equation f of, d square plus a square of y is equal to 0, and auxiliary equation is f of m is equal to 0. So which will give you m square plus a square is equal to 0. So it's a quadratic equation. So a is some constant, real constant. So solving this by the formula, we will get the roots as m is equal to plus a I minus ai, or writing that in the standard form, it is 0 plus ai m1 and m2 is 0 minus ai. Now compare this root with alpha plus I beta and alpha minus I beta. So we can identify the values of alpha and beta. Alpha is the real part, which is 0. Beta is the imaginary part, which is a here. So substitute this alpha and beta in yc, that is equal to e power alpha x into c1 cos beta x plus c2 sin beta x. Alpha is 0 and beta is a here. So it will give you yc is equal to c1 cos ax plus c2 sin ax. Now this is compared with c1 u of x plus c2 v of x. So c1 into u of x, okay, so u is cos ax, c plus c2 into v of x, so v is sin ax. So comparing, u is equal to cos ax and v is equal to sin ax. So we need the derivatives of this to find the Wronskian. So u dash is minus sin ax into a, and v dash is cos ax into a. For the particular integral part, we apply method of variation of parameters because the function on the right hand side is tan ax. So w is calculated as determinant of u v and u dash v dash. So substitute all the four functions. U is cos ax, v is sin ax, and u dash is minus a into sin ax, v dash is a into cos ax. So expanding the determinant, we'll get a into cos ax into cos ax minus of minus a into sin ax into sin ax. So it will a as common, cos square ax plus sin square ax. Okay. So cos square ax plus sin square ax is 1, you'll get a into 1 a. Obviously this is not equal to 0 in our case. Now by the method of variation of parameters, yp is given by yp is equal to a of x into u of x plus b of x into v of x. So we have a of x is equal to minus integral vq by w dx, and b of x is equal to integral uq by w dx. So substituting these functions, we find a and b. So a is equal to minus integral, v is the function in yc, which is sin ax, this is v, and q is the right hand side, which is tan ax, and w is a. So minus integral sin ax tan ax by a dx. So tan ax, okay, is sin ax by cos ax. 1 by a is a constant, it's separated from the integral. So the integrand will give you sin ax into sin ax by cos ax. So multiplying these two, we'll get sin square ax. So a of x is equal to minus 1 by a integral sin square ax by cos ax dx. So we have to integrate this after some trigonometric relations are used. So sin ax, sin square ax in the numerator is written as 1 minus cos square ax, and divide each term in the numerator by denominator. So a of x is equal to minus 1 by a, 1 divided by cos ax minus cos square ax divided by cos ax into dx. So here you can cancel cos ax. So a of x is equal to minus 1 by a, reciprocal of cos ax is secant ax minus cos ax dx. So we know the integration of secant ax, we know the integration of cos ax. So a of x is equal to minus 1 by a, integration of secant ax is log secant ax plus tan ax by a, because the constant is a, minus sin ax by a, integration of the next term. So again 1 by a is common in the denominator. So a of x is equal to minus 1 by a square log of secant ax plus tan ax minus of minus plus sin ax by a square. So this is a. Now b is given by integral uq by w dx. So u is cos ax here, q is tan ax here, W is A. Now again write tan Ax, taking 1 by A outside the integral, tan Ax as sin Ax by cos Ax. So cos Ax can be cancelled here. So B of x is equal to 1 by A into integral sin Ax dx. So integration of sin Ax is minus cos Ax by A. So B of x will give you minus 1 by A square cos Ax. So substitute all the four functions A, U, B, V in Yp. So Yp is equal to, so A of x is minus 1 by A square log of secant Ax plus tan Ax plus sin Ax by A square into U cos Ax plus B is minus 1 by A square cos Ax into sin Ax. So after multiplying, so this will cancel and you will get Yp as minus 1 by minus cos Ax by A square log of secant Ax plus tan Ax. So the general solution is given by y is equal to yc plus yp, which is y is equal to c1 cos Ax plus c2 sin Ax, and yp is negative here, minus cos Ax by A square into log secant Ax plus tan Ax. Now as a summary, we have seen two cases for particular integral here. So one is when q of x is equal to x into v of x, we apply this integration yp formula as x minus f dash of d into 1 by f of d of 1 by f of d of v of x, where this expression is evaluated from the right, that is this part is evaluated, 1 by f of d of v of x is evaluated, and this is operated on both the terms one by one. And next we have seen the general method to find the particular integral, that is method of variation of parameters for a second order linear differential equation. So here q of x can be any function. So we have seen the example for tan Ax. So the function can be secant, the function can be cosecant, the function can be cot, the function can be logarithmic function. Okay, for all these functions on the right hand side, we can apply this method of variation of parameters to find yp. So yp is given by a of x into u of x plus b of x into v of x, where a is given by this expression, b is given by this expression, and u and v are obtained from yc, and w is the Wronskian of u and v. So this is one of the important methods to find the particular integral for a second order linear differential equation, method of variation of parameters. Thank you.